Right now, hidden beneath one of the coldest and supposedly most stable stretches of Antarctica, scientists have discovered something genuinely strange. A network of channels carved into the underside of a floating ice shelf that are actively trapping warm ocean water in exactly the places where it does the most damage. And researchers say current climate models are missing this process entirely. A study published this year in the journal Nature Communications, led by researchers at the IC3 Polar Research Hub in Norway, found that these hidden channels beneath the Fimbulisen Ice Shelf in East Antarctica can amplify localized melting by roughly an order of magnitude, meaning 10 times more melting in specific spots than a smooth, unchanneled ice base would ever produce. Even more unsettling, this is happening in East Antarctica, the exact region scientists have spent decades treating as the cold, stable half of the continent compared to the more vulnerable West. Today, we are going to break down exactly what researchers found beneath the ice, why this specific discovery is considered so strange, and what it actually means for how fast Antarctica's ice might be changing. No exaggeration, no doomsday guessing, just the data, the physics, and the real stakes. Drop a comment right now. Have you ever seen footage of Antarctica's ice shelves or wondered what is actually happening underneath all that frozen surface? Tell me what you thought. So many of you have seen those images circulating online, and I always want to hear what stood out to you. If you want to know the moment new research on this comes out, subscribe right now. It costs nothing, and a thumbs up tells the algorithm to put this in front of people who genuinely want the real science. Let us get into it. Ice shelves are massive floating extensions of glaciers, essentially the point where a glacier's ice slides off the land and out over the ocean surface while still remaining physically connected to the ice sheet behind it. They function like enormous doorstops. Their bulk and friction against the surrounding coastline and seafloor helps hold back and slow the flow of the much larger mass of land ice sitting behind them. When an ice shelf weakens or thins, it loses some of that holding power, and the glaciers behind it can begin sliding into the ocean faster, directly raising global sea levels in a way that ice already floating on the water's surface does not, since floating ice displaces its own weight in water and does not raise sea level when it melts. But land ice sliding into the ocean for the first time absolutely does. This is exactly why the structural health of ice shelves has become one of the most closely watched variables in climate science, and why the Intergovernmental Panel on Climate Change has previously flagged weakening polar ice shelves as one of the single largest sources of uncertainty in global sea level projections. The research team behind this new discovery, led by Tor Hatterman and Qin Zhou, focused their attention on the Fimbulisen Ice Shelf, a section of coastline in East Antarctica that has traditionally been viewed as one of the more resilient, cold-buffered parts of the entire continent, precisely the kind of place scientists did not expect to find a dramatic new melting mechanism hiding underneath. To study what was actually happening beneath the ice, the team combined an extremely detailed map of the ice shelf's underside with a high-resolution computer model simulating the ocean cavity trapped between the ice and the seafloor below it. What they found is genuinely strange. In the most literal sense, the shape of the ice shelf's underside is not simply a passive surface sitting on top of the ocean. It actively shapes how seawater circulates beneath it. Where deep channels exist carved into the ice from below, ocean currents form small, localized circulation patterns that keep warmer water trapped directly against the ice, rather than allowing it to flow away and mix with colder surrounding water the way it would beneath a smooth, unchanneled surface. Lead author Tori Hatterman described the core finding directly, explaining that the shape of the ice shelf underside is not just a passive feature, it can actively trap ocean heat in exactly the places where extra melting matters most. That trapped warmth does not spread its damage evenly, it concentrates. And the research team measured that melting rates within these channels can increase by roughly a full order of magnitude in specific locations compared to the surrounding ice, an intensification driven entirely by the geometry of the ice itself, rather than by any dramatic new source of ocean heat arriving from elsewhere. Hatterman was specific about how small a temperature shift is actually required to trigger this effect, noting that even small amounts of warmer water can substantially increase melting once it becomes trapped within these channel structures. Co-lead author Qin Zhou added a detail that reframes how scientists should think about supposedly stable cold water regions of the continent, pointing out that even modest inflows of warm or deep water can have a large effect once the ice shelf base is channeled, meaning ice shelves researchers usually categorize as cold and therefore safe may actually be considerably more fragile than anyone previously assumed. This is where the growing part of the story becomes genuinely important, because the researchers describe a feedback loop that compounds on itself over time, rather than staying contained. As melting intensifies specifically within these channels, the channels themselves grow deeper and wider, which increases their capacity to trap even more warm water in future seasons, which accelerates melting further still, causing the ice shelf to thin unevenly across its structure rather than uniformly across its whole surface. Uneven thinning is a particularly dangerous pattern structurally, because an ice shelf's overall strength depends heavily on maintaining consistent thickness and structural continuity across its width, and channels weakening specific stress-bearing sections can undermine the shelf's stability disproportionately, compared to how much total ice volume has actually been lost. Haderman was blunt about the practical consequences of this process continuing unchecked, warning that current climate models do not capture this effect at all, which means models built without accounting for channelized melting risk significantly underestimating just how sensitive these cold East Antarctic ice shelves actually are to even small changes or warming in the coastal waters surrounding them. And crucially, the researchers noted that these kinds of changes have already been observed in the region and are projected to increase further in the years ahead, meaning this is not a purely theoretical risk sitting in a future model projection. It is a mechanism actively operating in present-day conditions, along a coastline scientists had previously treated as comparatively safe. To verify their findings were not simply an artifact of computer modeling. The research team incorporated years of earlier field observations collected directly from the region into their analysis, and Haderman himself has personally spent hundreds of days living and working on Antarctic ice shelves during past research expeditions, giving the study a foundation grounded in direct physical measurement rather than modeling alone. The broader implications extend well beyond this single ice shelf. If comparable channel structures exist beneath other sections of East Antarctica's coastline, and researchers have every reason to expect they likely do, given how common channelized ice shelf undersides are across the continent generally, then the true vulnerability of what has long been considered the safer half of Antarctica may be substantially underestimated in the climate projections currently used for coastal planning and sea level rise forecasting worldwide. This connects to a broader pattern of unexpected discoveries emerging from beneath Antarctica's ice in just the past year alone. Researchers using earthquake data have separately traced the origins of a long-documented gravity anomaly beneath the continent to slow tectonic rock movements occurring tens of millions of years ago, while a completely different research team recently mapped a vast, previously unknown network of enormous basins hidden beneath ice that exceeds 3 kilometers in thickness in some locations. Discoveries that collectively point to the same conclusion: Antarctica's subsurface structure remains far less understood than most people assume, and each new mapping effort keeps revealing features that reshape how scientists think this ice sheet will actually behave as ocean temperatures continue shifting. So what does the science genuinely say about how fast this specific process is likely to unfold? Researchers were careful and precise in their public statements, describing a mechanism that intensifies existing vulnerability rather than announcing an imminent collapse timeline. The honest scientific position is that this discovery raises the probability that current sea level projections are too conservative, not that a specific catastrophic threshold has already been crossed. What remains genuinely uncertain is exactly how widespread channelized ice shelf undersides are across the rest of East Antarctica's coastline, and how quickly the feedback loop these researchers identified will actually compound in ice shelves beyond the one they specifically studied. If you are following this story because you live somewhere along a coastline anywhere in the world, the practical relevance is direct, since accelerated ice shelf thinning in previously considered stable regions directly feeds into how quickly land-based glacial ice enters the ocean. Meaning sea level rise projections built without this mechanism may need meaningful revision as more research teams apply this same detailed mapping and modeling approach to other sections of the continent. Final thought. What makes this discovery genuinely strange is not that Antarctica's ice is melting. Scientists have documented that process extensively for decades. It is that the melting is being actively accelerated by the physical shape of the ice itself, a self-reinforcing structural feature hiding in exactly the region assumed to be the most resistant to this kind of change. The channels beneath Fimbulisen Ice Shelf were not created by some external force suddenly attacking the ice. They are a physical characteristic of the ice shelf's own geometry, quietly trapping just enough warm water to grow themselves larger over time. A feedback loop scientists only recently gained the tools to properly observe and measure. We will keep tracking every new mapping study, every ice shelf model, and every research expedition as this picture continues to develop. Subscribe so you do not miss it, and leave that comment below. Did anything about how Antarctica's ice actually behaves beneath the surface genuinely surprise you today? Because understanding what is happening at the literal bottom of the world is how the rest of us stay informed about the coastlines every single one of us eventually depends on. Let us get this one to 5,000 likes. See you in the next one.